Have you ever stopped to think about the invisible architecture that, basically runs our modern lives? I'm talking about the weather forecast you check every morning, the GPS that gets you home. It's all powered by this incredible network of objects just silently flying way, way above our heads. So today, we're going to pull back the curtain and take a look at how this amazing network of satellites actually sees our world.
All right, here's our game plan. We're going to tackle this in 5 parts. First, we'll cover the absolute basics. What even is a satellite? Then we'll get into their orbits, their altitude, and the very cool jobs they do. And to wrap it all up, we'll see how all these pieces fit together to create this incredible web of technology that literally wires our world from above.
Okay, let's dive right in. First up, the satellites above us. Before we get into the complex stuff, we need to agree on what a satellite actually is. So let's start with a really clear definition.
At its heart, it's pretty simple. A satellite is just any object that's locked into an orbit. That curved path is the whole secret. You see, thanks to gravity, it's constantly falling toward, say, the Earth. But because it's also moving sideways so incredibly fast, it just keeps missing. It literally falls around the planet. Kind of cool, right?
And that brings us to a super important distinction we have to make. On one hand, you've got natural satellites, like our moon, which has been doing its thing for billions of years. But then you have the artificial, human-made ones we're really talking about today. Things like Sputnik, the little guy that kicked this all off, which we have to launch into space on rockets. So, now that we know what they are, let's look at how they move through space. The first way we can really classify a satellite is by its orbit, that very specific path it follows in its own unique celestial dance. First up, we have geostationary satellites. The best way to think about these is as Earth's perfect dance partner. They orbit at the exact same speed that our planet spins. So from our perspective down here on the ground, it looks like they're just hanging out in one fixed spot in the sky. And this was an absolute game changer. For the first time, you could just point an antenna at one spot and get a continuous signal. This is what made live, global TV possible.
Now, to pull off that perfect synchronization, a satellite has to be at a very, very specific height. 36,000 kilometers. It's at that incredible distance, and only that distance, that its orbital speed perfectly matches Earth's 24-hour spin.
Then, on the complete other end of the spectrum, you have sun-synchronous satellites. Instead of matching Earth's rotation, these guys are synchronized with the sun. They travel in a polar orbit, basically from the North Pole to the South Pole, and they're designed to pass over any given spot on Earth at the exact same local solar time. So it might fly over London at 10:30 a.m., then later fly over Chicago at its 10:30 a.m. Having that consistent sunlight is just perfect for observing our planet. And this table really lays out the difference, doesn't it? I mean, just look at the altitude. Geostationary satellites are way up there at 36,000 kilometers, taking a whole day to go around once. Sun-synchronous satellites are much, much closer, and they whip around the Earth in about 100 minutes. And this difference in height and speed directly leads to what they're used for. One is for constant communication, and the other is for getting a detailed look at our planet.
And that difference in altitude is the perfect segue to our next way of classifying satellites. Because it's not just about the path they're on, it's also about how high they fly. You can almost think of it like a ladder to space, with different jobs happening on each rung.
So we've basically got 3 main rungs on this ladder. The closest one to Earth is LEO, that's low Earth orbit. Moving up a big step, you get to MEO, or medium Earth orbit, and then at the very highest altitudes, you've got HEO, or high Earth orbit.
Now, flying close to home in LEO has some serious perks. You get a much stronger signal and way less lag, which is fantastic for things like satellite internet. But of course, there's a trade-off. Because they're so close, they're actually getting dragged down by the tippy top of Earth's atmosphere. This atmospheric drag slows them down over time, which shortens their lifespan. And since they're moving so fast across the sky, you need a whole bunch of them, a whole constellation, to get continuous coverage. And probably the most famous resident of LEO is, of course, the International Space Station.
Okay, let's climb up to that middle rung, MEO. This is the absolute sweet spot for our navigation systems, like GPS. And why is that? Well, from this altitude, the satellites are visible in the sky for a much longer time. We're talking several hours at a time. That makes them way more reliable for pinpointing exactly where you are.
And finally, we get to the top, high Earth orbit, or HEO. And this one has a really unique feature. It's the only one of the 3 that isn't a perfect circle. It actually follows an elliptical, or oval-shaped path. This special orbit lets a satellite kind of linger for a really long time over one part of the world, which is ideal for things like military surveillance or for communicating with remote polar regions.
Okay, so we know their path and we know their altitude. That brings us to our final and maybe most important way of classifying them. What do these things actually do? What are their space-age jobs?
When you boil it all down, they really have four main jobs. Some are basically our global messengers, handling all our TV, phone, and internet communications. Others are our navigators, providing the positioning for systems like GPS. A third group, they're our observers, constantly mapping the planet and tracking our weather. And finally, you've got the ones that serve really specialized military and scientific missions, everything from surveillance to deep space research.
And that really gets at the incredible power of this technology. You know, when we talk about navigation, we are talking about mind-blowing precision. A whole network of satellites up there in medium Earth orbit can work together to triangulate your location on the globe to within just a few meters. That little blue dot on your phone? This is the magic that makes it happen.
So for our final section, let's put all the pieces together. We've looked at orbits, altitude, and all their different jobs. So how does this all combine to, well, wire our world from above?
All right, to really picture how this all works together, a few quick terms are super helpful. We already know the orbit. That's the satellite's path. Now, as it travels, the area on the surface that it can see at any one time is called the swath. And the nadir point? That's just the spot on the ground directly underneath the satellite. Simple as that.
So when you put it all together, you realize it's not just one satellite doing one job. It's this beautiful interconnected web. You've got the geostationary satellites way out in Hio handling our communications, while the sun's synchronous satellites are buzzing around in Leo monitoring our environment, and that whole constellation in Mio is guiding our way. Each one is perfectly designed with a specific orbit, a specific altitude, and a specific job, and they're all working together like a symphony.
And that really leaves us with a huge question for the future. As our world becomes more and more reliant on this invisible architecture, how do we make sure that we manage this incredibly vital resource? How do we keep it stable, keep it secure, and keep it accessible for all the generations to come?